is given by Tommaso Benacchio, and he's talking about multi-level time integrators for large-scale atmospheric flows.
Thank you, Andreas. So I'm reporting here on the progress I've been doing in my PhD work that I do in the Berkeley group at Freie Universität Berlin. And let me first thank the Newton Institute for the great opportunity that it's giving me in these weeks to work in a very inspiring and productive framework. And next, some credits. Dublin Research School and Berlin Mathematical School that provide a great framework for graduate studies in Berlin. So that's an outline of my talk. I'll give some motivation, then describe the model that we are simulating, give some preliminary results, and spend some words on the work that I will be doing. So the motivation for a compressible multiscale solver is basically that, as we all know here, dynamic processes in the atmosphere occur at very different spatial and temporal scales. And in the atmosphere is weakly compressible in the sense that most flows develop at low speed with respect to the speed of sound, and the Mach number is a quantifier of the compressibility effects in the flow. This is a picture of what we're talking about. So basically, if we think about an oscillation we have space in the x-axis and time in the vertical axis, and if we think about an oscillation with period t, that brings about advection of scalars and generation of elastic waves. These two processes are apart by a factor that is actually the Mach number. So there is a scale separation in this setting, and gravity processes will be somewhere here in the middle, but for this talk we focus on this this regime. And so the problem with sound waves, as we learned from the last 2 days, is that they are thought to be physically unimportant, but they provide for technical difficulties in explicit discretizations of the equations, in that they impose a time step for stability constraint dictated by the speed of sound, which in our case, as we saw, is much larger than the typical speeds encountered in advective processes in the atmosphere. So one could go and chop them from the beginning in adopting soundproof models, so inelastic models, or what is done in numerical weather prediction, hydrostatic models which filter vertically propagating sound waves. And last week we've heard, and also this week on recent interesting investigation on models which could keep the features on both models in a unified framework. On the other hand, if one wants to retain the fully compressible model, then the treatment and basically the suppression of small-scale fast sound waves would be handed over to the numerics, and virtually all numerical models that simulate the fully compressible equation contain an implicit part which handles the fast processes. So the thing with the problem with implicit discretizations is that if they are applied in not a sensible way, they could give rise to bad dispersion properties in that waves can be artificially slowed down, as was effectively pointed out by these Stefan Vater and contributors publication last year. So in this framework, our target is to simulate a fully compressible model in a semi-implicit fashion with a conservative finite volume scheme in order to maintain second order accuracy in all the part of the model, remain consistent with the soundproof limits that we've learned about, and from this full-fledged setting, investigate different effects of dynamic processes at different scales. So how do we go for that? We consider the compressible order equation, so conservation of mass, momentum, and energy, where we got to know this p variable yesterday, which is basically an elaboration of the pressure equation, and it is related to the pressure with the ideal gas equation of state. And of course, we have to assign initial and boundary conditions, and for the time being, we neglect contributions from the Coriolis term. So this alpha switch is basically what brings us from the pseudo-incompressible model, which has alpha equals 0, and then the energy equation becomes a divergence constraint in that the p variable we consider a time-independent leading order pressure variable, and we have no evolution for the p variable in practice. So first we make explicit the relationship between the p variable and the pressure by developing this derivative, which will be useful in the following. And we describe now our numerical method, which is a fractional step projection method. So what happens here is that it is basically a finite volume conservative solver. And in a predictor step, we solve an auxiliary hyperbolic system. The fluxes are here upwind with linear reconstruction. And then we have two corrections, in which the first correction corrects the fact that this auxiliary system is not compliant with the fluxes that are computed from in the predictor step are not compliant with the constraint on the p variable. And in the second projection, we correct the use of the old time level pressure in the predictor step, and with that we correct the momentum flux and the old time level pressure. So finite volumes, u vector of conserved variables, f numerical flux, and this is basically the scheme. The star denotes the variables at the end of the predictor step. And for time integration, we have a second order Runge-Kutta scheme with now the big U denotes approximations of cell averages, and the big F approximations of the numerical flux. Sure. That was just a rewriting of the equation. Sure. In fact, this is the equations for the predictor step, in which basically the cell averages are updated with fluxes at consistently second order at half-time level, but the pressure in the momentum equation is the one at the old time level. So the problem with this is that on the one hand, as we said, the velocities do not comply with this constraint, and the all-time level pressure is used. So we have to correct these relations, and we do it through two corrections. So in the first correction, we integrate the momentum equation over a half time step, and we decompose the pressure in the all-time level and the contribution that we will have to obtain to comply with the divergence constraint. And then we use the old chain rule and interpret the derivative of the pressure as our pressure increment over the time step. And this, inserting this relation multiplied by the potential temperature plus this in the constraint, we obtain a Helmholtz equation where basically the classical Poisson equation that we have in the pseudo-incompressible model is modified through the addition of a zero-order term. There are a couple of things to say about this equation. So the first is that we can transform it through some computations and see that actually this zero-order term is a function of the speed of sound and then in turn of the Mach number, so that keeping the CFL number for advection constant and letting the Mach number go to 0, we basically retrieve the pseudo-incompressible model, and this is what we expect from our model. And also a thing we are working on is the compliance of this equation with a classical finite difference discretization for the hyperbolic equation for the pressure, which is what one would expect in a compressible model. The pressure, we have pressure waves in a compressible model, and we want to prove on paper that this is handled by our model. So with the solution of the first projection, we correct the advective fluxes and the interfaces, and then we still have the all-time level pressure used in the momentum equation, and we have to do a second projection. So as before, I omit the details here, but we integrate now over a full time step. We now have our constraint, which now second order has to be considered here inside the divergence. And again, we replace everything and we obtain a second Helmholtz equation for the nodal pressure increment that at the end of the time step is added to the pressure after the correction of the momentum fluxes. And this retrieves a full second order scheme in our numerical model. So how did we implement this? We have a C++ object-oriented code which is fully parallel and is based on the Samurai static adaptive mesh refinement library, and uses hyper solvers for the linear systems. And now a note on efficiency: we didn't do yet real computational cost studies, but we see that the actual overhead of what we are doing over the pseudo-incompressible model is just the addition of the diagonal term in the linear system matrix. So we basically can model, we're looking forward to modeling a full range of waves in our model with respect to the pseudo-incompressible model with an overhead which is at the moment limited. So preliminary results on this case, we want to validate our method, and basically what we want to check is that in a low speed case, the differences between our model and the pseudo-incompressible model are negligible, and that our model can represent the evolution of the p variable, so which is a thing that is not featured in the pseudo-incompressible model. And to do that, we consider a low-speed traveling rotating vortex on a doubly periodic unit square. I don't know if you can see the color bars. Anyway, it's a positive perturbation for the density, and we have a the vortex is rotating anti-clockwise with basically the maximum of the velocity on the boundary. The contours here are 0.25 apart with a minimum value of 0 and a maximum value of 1. We superpose on, well, this is an exact solution in the incompressible case. And on top of this, we impose a constant background flow. So basically, we consider a diagonally traveling vortex. And this is the initial distribution for the pressure, low pressure in the middle. And reference quantities, we have density. Actually, in this test case, we had 0.5 reference density. We wanted to stick to these values, but then we looked and we said, okay, but with the reference pressure, like 1,000 hectopascal, we would land on Venus, and actually that's what we did. So we are working with 700 kelvins. But we plan to go back on Earth soon. So, and the Mach number is, for this test case, on the order of 10 to the minus 3. So we expect negligible difference between the pseudo-incompressible and the fully compressible model. The initial distribution for the p variable is obtained from the pressure one through the equation of state. And we run our scheme with 192 by 192 cells. And the time step is determined by an imposed CFL number for advection. And in the simulations that I'm showing, I'm using 0.5 CFL number for advection. And this corresponds actually to a CFL number for acoustics of 110 on Venus. On Earth, it would be something like 70 or something. So what we expect from this guy is basically that after one period, the thing basically comes back to the initial state because we have a doubly periodic domain unit velocity, and one period density pressure in the compressible case, pseudo-incompressible case, I norm, no sensible difference. 2 periods, density, pressure, compressible model, pseudo-incompressible model. Again, no sensible difference, but the thing that we worked the hardest on was actually the simulation of the p variable and the pseudo-incompressible model. What happens in the pseudo-incompressible model is that through the two projections, the increments of the p variable are basically projected away, and we have a constant value for the p variable. In our model, we expect something like this to happen. So basically, we want the initial distribution of the energy, which was this, to be the same also at the first and at the second period. And this is one period, this is 2 period, not perfect, some asymmetries here, but I would say not bad to start with. And what I plan to do next with this thing is to do convergence studies for different Mach numbers, and also to do an acoustic wave test case to see that our system can actually handle hyperbolic cases. So in summary, we described the discretization of a fully compressible semi-implicit model for the simulation of multiscale atmospheric processes. the features of this model is that we constructed that starting basically from a pseudo-incompressible philosophy, and so this is, by implementation and construction, compatible with a soundproof model. It is conservative and second-order accurate, and what we plan to do next is to use this model as a platform for the study of the interplay between different dynamic processes at large scales. And how we want to do this is to consider, again, the scheme introduced by Stefan Vater and collaborators, which is a multi-level time, introduces a multi-level time discretization in a multi-grid fashion. So in that paper they simulate linear acoustics, and they consider different implicit discretizations. They do some dispersion studies, and they basically blend different implicit discretization through a scale selective decompositions of the variable. And by exploiting the good damping properties on one hand, as we heard last week at the PDEs in the talk, they use trapezoidal and backward difference. So on the one hand, they have schemes that can damp short waves effectively, and on the other hand, they use schemes that are less dispersive and can simulate transport of longer waves accurately. And by suitably blending these two approaches, the idea is to reach control over the simulated and the unresolved scales, in the sense that we want, given a time step, we want the unresolved scales to be damped away and the simulated scales to be accurately transported. And the idea is, of course, having a fully compressible model to do all of this on the sphere, and we are considering spherical grids, in particular the ones introduced by Donna last week at the PDs. And that's it. Thank you.
Other questions? Stefan?
So you use collocated variables for...
Yeah, sorry, I didn't. So basically, all the variables are at the cell centers, apart from the pressure, which is at the nodes.
So in the zero Mach number limit, do you reduce to approximate projection methods, in effect? The lack of staggering, you have, you can't get the projection exact on the centered field.
Yeah, we are planning also about the possibility of doing exact projections in that we could keep track of also the gradients of the quantities, but we have not implemented that.
Okay.
We have Stefan and I have a paper on how to do that in that same framework. Okay. And the key is that you not only correct the mean momenta in the grid cells, but you also correct the slope of momentum in the projection step. And then you can actually make it an exact projection, for which we proved some in-soup stability properties of the projection step.
Other questions?
Your test case considers a large-scale vortex, and therefore is not a particularly strong test of your scheme in terms of how well it handles small-scale generation of possibly numerical noise. And I would suggest trying to use a sharper vortex flow initially, or maybe a strip of vorticity, for instance, that could go into Rayleigh instability and see what happens.
Sure.
Then you generate the whole spectrum of waves.
Sure, that's quite smooth. That's a quite smooth test, but we just want, actually, the main point here was, well, of course, this, but more this. So we wanted to see our hyperbolic transport of the p variable. But sure, we want to further investigate also the aspect that you stressed.
I guess you're still trying to resolve everything, right? I mean, it's in a sort of a multi-scale fashion, right? Is that sort of?
Well, not.
I mean, there's nothing explicitly actually removed, right? I mean, there's still everything in principle there.
Yeah.
Did I get it wrong? No.
Yeah.
So,
But
then you must be slowing down something, right? Because you said initially you don't slow down stuff, or it's not good. Let's put it this way: so that it's not a good idea to slow things down by implicit methods.
Sure.
Do it.
That's
I
why we want. Yeah, I mean that's the first steps. Then we want to use a more accurate solver to handle.
You would need some inner time steps. I mean, then you need. I'm getting this wrong? I mean, have you done a dispersion relation study for your method? So how does the dispersion compare to the exact dispersion relations? Analytic dispersion, in a linearized setting.
Let me answer this.
Yeah.
So you're getting exactly at the point that we're after, which is to say we want to make large time steps because on the small scales, advection is what dominates.
Right,
And at
sure.
best, we need the wave propagation of the acoustics on very large scale. So we
right.
need advective time scale CFL numbers of
Right.
order unity. But then at the same time, when we use, say, a symplectic integrator for everything, then we have that problem that the small scale generated whatever perturbation it is never goes away and is slowed down and sits on a grid and doesn't do it.
Right.
So what we want is a scheme that the large scale propagates the large scale features with an energy preserving scheme.
Right.
Whereas for the small scales that we know we do not resolve because we are making a large time step, we want to damp them away and have the scheme approach a pseudo-incompressible approximation.
But in what sense? I mean, you damp them away or you project them away properly?
Basically, this scheme, depending on how you do the blending, it either rapidly damps them away or on the finest grid even projects them away.
Okay, but how is that still second order? You say the scheme overall is second order.
Yes, this is a trick that is in the multi-level time integration scheme. For everything we do not resolve, we use backward in time information to generate the time derivatives. And so we actually do not throw away the second order accuracy for everything that's slow enough to be resolved. Everything that's faster than we can resolve it, it's projected away or damped away.
Right. I think it would be, I guess, useful to have I mean, I'm always...
Stefan did the dispersion relation since you
Oh,
asked that. And what comes out is that, in fact, for the relatively long waves that we can resolve with the time step, we're with the dispersion relation pretty close to the diagonal as far as the speed goes.
Right.
And the damping coefficient is pretty much unity, so we reproduce the amplitudes. But then when the dispersion curve deviates in terms of the speed from the diagonal, the damping curve goes down.
Right. But how much does it differ from sort of off-centering schemes?
Well, we have
They
much
formally,
better-
I mean, of course, they're
Yeah.
formally not second order, right? I mean, they close to second order,
First,
right?
they are not second order for the slow modes, even, because they
Well,
are
I mean,
not
if you
second
look at
order.
the dispersion relations, you always, I mean,
But they are not second order, period, right?
yeah.
So, our scheme is second order.
Right.
For everything that we resolve, we actually get second order. That's one difference. And the second difference is we have much more tighter control on what happens on the small scales. We can actually force the scheme to produce pseudo-incompressible behavior on the finest grid that we use. Or
And
whatever.
one thing that I guess in metrology, I mean, I know that the UK method has always been, because whenever the Helmholtz problem occurs, you need some sort of background state you introduce, right? About your linearized. And in your case, I think it's the choice that you use the Duran equation down there. I think that must implicitly define somehow a background state. Because it is a linearization. If you get a Helmholtz problem, you have done somehow linearization about a state.
We will linearize around the current state.
Right. So you
Not
just
the
take
background state.
it's
It's
the
the
current
current
state.
state.
Okay.
Further questions? seems not the case. So let's thank Tommaso again.